Hello there. We are going to talk about exponential functions today. And um, this is actually something that is very useful when we talk about something that grows exponentially or something that decays exponentially. So, what makes an exponential function that? It is where your variable x is the exponent. You have a base, we'll call it b for base. Sometimes you're going to have some type of actually, you can have lots of transformations on it. But basically, a is just some constant. It can be positive, negative, fraction, doesn't matter. But it's kind of helps with the steepness. If something grows exponentially, it grows very, very fast. If something decays exponentially, it is decaying very, very fast as well. You have seen exponential decay in science classes, likely, when you talked about half-life. That is an example of exponential decay. Exponential growth, I always liked it when we were in COVID. I loved to talk about exponential growth because the number of cases was growing exponentially when one person had the virus and they were in contact with other people, it grew just, we might say tenfold, it grew exponentially. So anyway, there's lots of things out there. Our gross national product, our national debt, lots of things grow exponentially. Population also grows exponentially. Um, anyway, let's just get right on to it. What makes it growth? What makes it decay? Not all exponential functions are one or the other. When you start flipping them vertically, they're no longer. We call that reflected growth or reflected decay if they're flipped vertically. Horizontal flip, if you have a horizontal reflection, your growth turns into a decay or vice versa. It depends on what you're started with. We're going to do a lot of graphing today in this video, and we're going to do a lot of transformations. So a lot of it is going to be stuff you've seen before on your other functions, and so we're just going to need to make that connection to exponential growth and decay. We have an asymptote involved here. We're going to plot y-intercepts. We're going to find one other critical point. For the parent graph, your range is going to be 0 to infinity. For all exponential functions, your domain is all real numbers. It is continuous. There are no breaks in the graph, so no holes or vertical asymptotes. So let's dive on in here. What makes it growth? It means your base is bigger than 1. And then decay is when b is a fraction between 0 and 1. Notice how we're not talking about b being negative because b is never going to be negative. Just so you know, b is always going to be greater than 0. So growth if b is bigger than 1, decay if b is a fraction between 0 and 1. So we're going to take a look at these 6 examples here, and we're going to tell whether they're going to be growth or decay. So you just need to look at b. The number out in front does not change whether it's growth or decay unless that value is negative, like there's a negative out in front. But if just some normal constant, that's just going to make it grow faster. That's all. Or decay faster. Okay, so 2/3 is between 0 and 1, so that is decay. 3/2 is 1.5, so that's bigger than 1, so this is going to be a growth function. This one has asterisks on it because it has a negative exponent. So we actually have to think of this, go back to what happens when you have a negative exponent. When you have a negative exponent, it takes it to the bottom of a fraction, and then this becomes a positive exponent. So now we have decay. And again, you don't need to look at A, the number out in front. Okay, the number out in front of D is 1, so it doesn't really matter, but 3 is going to be growth. 9 is going to be growth here, and this will be decay. So the only tricky one was C because it had a negative exponent. All right, so we're going to graph these exponential functions, and let's take a look at see how they look on a coordinate plane. All right, so if I were to do an XY table, and I choose values of x and plug it in, how about 0, 1, -1, 2, -2? How about those? Plug in 0, 2 to the 0 is 1. Plug in 1 to the first is 2. Plug in a negative 1, it's a half. Plug in 2, you get 4. Plug in negative 2, 2 to the negative 2 is 1/4. So we have 0, 1, 1, 2, negative 1, a half, 2, 4, and negative 2, 1/4. Now, what I want you guys to see here, I could put down here negative 10, right? That's going to be, sorry, to the negative 10, which is 1 over 2 to the 10th. That is not a negative number. It's a very, very, very small number, but it's never going to hit 0. And that's what's important that you understand about exponential functions, is that you're going to have some type of horizontal asymptote. Oops. And the graph is gonna, I don't know if I can do this. All right, that's not horrible. All right, arrows on the ends. And so it's curvy, it's supposed to be curvy, but make sure you understand, like, let's say x is 3, that's gonna be 8. So when I'm at 3, I'm all the way up here at 8 already. So it grows very fast. Okay, 2 to the 4th is 16. So it's, and you know, if we had a graphing calculator, it would look very vertical up here, but that's just the way it would look on a calculator or Desmos. So let's go ahead and answer these questions here. The domain is always going to be all real numbers. The range, 0 to infinity. Notice the parenthesis, it's never going to hit 0. I can put in a negative 1 million and I will still not get to 0. It'll never cross it. Your y-intercept is 0, 1. Your asymptote is a horizontal asymptote at y equals 0. As x goes to the left, y is approaching 0. As x goes to the right, y is approaching positive infinity. And then these graphs are either going to be increasing or decreasing. They'll never be both. From left to right, this is increasing. Not going to be decreasing, so just put a dash or none. Okay? All right, so that was exponential growth. As you can see, as x gets bigger, y gets bigger. All right, then we go ahead and do this decay problem. I'll do a XY table over here. How about that? We'll do the same numbers. Plug in 0, you get 1. Plug in 1, you get a half. Plug in a negative 1, you get 2. Plug in 2, you get a fourth. Plug in a negative 2, you get 4. I can go as far right as I can go. If I put in 1 million for x, you will still never get a negative number. It'll be, oh my gosh, sorry. Holy moly. So it approaches the asymptote, just kind of like rational functions did. You go towards the asymptote. Okay, arrows on the ends. Sorry, that was a terrible graph. That's the way it's going to be, guys. Okay, y-intercept, 0, 1, asymptote, y equals 0. As x goes to the left, this time the y values are going up to infinity. And as x goes to the right, y is approaching 0. Now this one is decreasing from a negative infinity to infinity. This is always your domain. Okay, these answers are always going to be your domain. Okay, that's not going to change. Okay, let's do some more graphing. All right, let's talk about transformations of exponentials. So a lot of this should look very familiar because we do it with our x squares, we do it with our cube roots. It doesn't matter the functions that we've learned. These are not changing, okay? So let's start with A. Let's start with A. A is your vertical stretch or compression. If A is bigger than 1, it's a stretch. If A is between 0 and 1, it's a compression. K is your vertical shift. It's your up or down. Remember, if it's plus 4, you take it up 4. What also is important about K is your horizontal asymptote. So it's always y equals k is your horizontal asymptote. Very important to know. So if you don't see anything there, you have y equals 0. If A is negative, you will have a vertical reflection. It flips over the x-axis. Okay, so and all of these affect the y values, if you remember that. Your A, your k always affect the y values. Okay, let's talk about what affects the x values. That's going to be your c. Actually, it says horizontal shift, so I got to read first. So H is your horizontal shift. It tells you to go left or right. Don't forget, you have to do the opposite. So if it's x minus 2, you go right 2. Again, if H is positive, you go left. If H is negative, you go right. C is your horizontal compression. Remember, this is kind of wacky. C, if C is bigger than 1, then you have a compression of 1 over C. So if you have, b to the 4x, that is going to be a compression of 1/4. Okay. If C is a fraction between 0 and 1, then it's a stretch of 1 over C. So if you have b to the 1/4 x, you're going to have a stretch of 4. So this is compression. I'm just giving you an example here. And this is going to be a stretch of 4. Okay, and then if C is negative, you have a horizontal reflection. That's going to change a growth to a decay function or vice versa. Okay, it's flipping over the y-axis. All right, so those affect the x values. The a and the k affect the y values, and that should be familiar. Excuse me. All right, sorry, I had a little tickle in my throat. Okay, so now we have 6 different parent functions here, and I want you to identify all the transformations. So the parent function is 4/3 to the x. So your base is 4/3. This is going to be a growth problem. And then looks like we have a vertical reflection. The negative's out in front. And it goes up 2. We have a vertical stretch of 2. And it goes right 1. The base is 3, obviously. Here, and that was growth. And this one over here is growth, but then it reflects vertically. So if it was growth and then it got reflected vertically, it's going to look like this, and we call that reflected growth. This is growth, this is decay. This goes left 2, down 1. Okay, now here's a function you've never seen before, and this is what we're going to learn in this unit. This is called exponential and logarithms. Log is short for logarithms. It doesn't really matter. If I called this Bob, if I called the function Bob of x, you should be able to tell me what the transformations are. This is right 5. It's because it's inside the parentheses, so it's right 5, up 1. You don't even need to know what the log is yet. You have a vertical compression of 2/3, down 8. And here you have a vertical reflection and a vertical stretch of 4, positive 4. It doesn't have a stretch of a negative 4. It has a stretch of 4. The negative refers to a vertical reflection. Okay, so we're going to get some practice in now, and just a few reminders as we go through here. When we graph them, we're only going to need 2 points. Okay, we don't need to plot a whole bunch of points. We only need 2 points in the asymptote. Remember, for the parent graph, it doesn't matter if it's growth or decay. The domain is always going to be all real numbers. Your range is going to be 0 to infinity. Your y-intercept is 0, 1. This is for the parent graph, and the asymptote is y equals 0. Another good point to use on the graph is 1b. Now, I'm going to add here, if this is growth, and -1, 1 over b, if it's decay. Now, I'm telling you this right now because this is a lot easier. This sometimes avoids fractions in our points. We'll come back to this in a second because right now we're still working with some of the descriptions of the transformations. But we need to learn how to come up with the 2 points. So we're going to use 0, 1, 1b if it's growth, or -1, 1 over b if it's decay. Okay, let's go ahead and get started. So what we're going to do is we're going to describe the transformation first. We're going to use the parent graph to the x for all of these. And then we're going to decide what our 2 points on our graph are supposed to be. All right, here we go. This has a horizontal reflection. And this is, all of these are growth, okay? So we're going to use 0, 1, 1, B. And your B is 2. Your base is 2. B stands for base. Okay, now the negative affects the x values, and you're going to multiply the x values by -1. So our 2 new points are going to be 0, 1, and a -1, 2. 0 times a -1 is 0. 1 times a -1 is a -1. So those are the 2 points that we're going to use on our graph. Here, this goes right 3. Sorry, I don't really like you abbreviating that. Let's try that again. Right 3. So we'll use 0, 1, 1b. If you go to right 3, you're going to be adding 3 to the x values. So our new points will be 3, 1, 4, 2. Here, this is right 7, down 5, so both, right 7 affects the x values. When you're going right, you're going to be adding 7 to the x coordinates, and down 5, you're going to be subtracting 5 from the y coordinates. So 7, -4, 8, -3. Here you have a horizontal compression of 1/2 and up 1. And I think if you remember 0, 1, 1b a lot, it'll be a lot easier if you continue to write it. So the 2 is affecting the x values, but you're going to be flipping that, so that's times 1/2. Horizontal stretches and compressions and vertical stretches or compressions are always multiplying. Up 1, so up and down and left and right is always adding or subtracting. So that'll be 0, 2, 1/2, 3. Okay, this is a vertical stretch of 4, left 3. Let's see, left 3, so subtract 3 from the x's, and times 4 on the y's. This one has 3 transformations, so it's a vertical reflection, down 5, and a vertical stretch of 2. So both of those things are affecting the y value, so is the -5. So everything is affecting the y values. All right, so when you do that, you have to remember PEMDAS, multiplication before addition and subtraction. So times -2 minus 5 times the -2 minus 5. So 0 is the same. -2 minus 5 is a -7. X stays the same. -4 minus 5 is a -9. So again, all you're going to do when we start to graph these in a sec, you just need to find the 2 points, okay? And then the k value is also a really important thing. I actually tend to graph the horizontal asymptote first. You can decide what you like to do first, I guess. Okay, so we have our base is 3. It goes right to up 1. So when I graph this, I have a horizontal asymptote at 1. And I might as well just do that. Okay, so what are our 2 new points? So I'm going to start with 0, 1, 1, B. Our base is 3. Okay, right 2 is affecting the x values, the up 1 is affecting the y values. So right 2 is a plus, and up 1 is also. So our 2 points are going to be 2, 2, and 3, 4. Pretty important, put the arrows on the ends of your graph, please. Now, this is a good one. I didn't know we had one so quickly showing up, but see, notice how I don't really have a y-intercept known. So we're going to have to calculate that. So you're going to plug 0, just like you would with any function that you've ever seen to find the y-intercept. You plug 0 in for x. So we get 1/9 plus 1. So 1 1/9 is what? 10/9. So it's a little bit more than 1. So it's really down here. I kind of missed it, but that's okay. You don't need to graph it. The other 2 points are fine. As x goes to the left, y is approaching 1. As x goes to the right, y is approaching infinity. And this is increasing everywhere, not decreasing. All right, now we have a decay problem now. So this will be a good time to start talking about that other type of point. We can do 0, 1, 1b, okay? But what I'd love to see you guys do is -1, 1 over b. Like I said, you can do 0, 1, 1b, but you have to deal with fractions, and that's no fun. Sometimes we have to deal with fractions here, but if I can remember when it's decay, when my base is between 0 and 1, 0, 1, -1, 1 over b, it helps me avoid fractions. All right, so the only thing that's happening here is down 2. That's the only transformation. So you're going to subtract 2. See how I avoided doing 1/3 minus 2? I mean, it's not a big deal. And I would accept it. 100% I would accept that answer. But this is sometimes it's just easier. That other point would be 1/3 minus 2 is 1 2/3. That's 5/3. If you want to have that. Okay, so this is down 2, so my horizontal asymptote, this is your HA, just don't forget. It's so easy to remember that. All right, so we have a point at 0, -1, -1, 1. So your graph goes towards the asymptote. If you want to graph, oh, that's not right. That's a negative. Sorry. Sorry about that. That's a -5/3. So it's over here somewhere. Right? 1/3 minus 2. Sorry, that was bad math. Okay, I could have gotten a little closer to that asymptote, but down here, but that's okay. All right, your y-intercept fortunately is given, or you found it already, so that's good. As x goes to the left, y is going up. As x goes to the right, it's going towards -2. This graph is decreasing everywhere. Okay, let's do a couple more graphs. We're almost done. All right, so what's our base is 1/4, so we have another decay. So I'm going to try the 0, 1, -1, 1 over b. This has a vertical reflection down 2. And so both of those things are affecting your y values. So multiplication first, times a -1 minus 2, times a -1 minus 2. If I chose to do the 1/4 times a -1 minus 2, so that's a -1/4 minus 2, so it's a -2 1/4. So that would be +1, -9/4. See, all right, so down 2, we have a horizontal asymptote at y equals a -2. And then my domain is all real numbers. Y-intercept is 0, -3. And again, if you didn't find it, if you didn't discover it in your 2 points, then you're going to have to go back to the original function and plug in 0 for x and evaluate. Okay? All right, so we have 0, -3, -1, -6. If you want to graph the 1, -2 1/4. Okay, so this one, you only have to graph 2 points. And as long as they're right, I don't care which two. Oh, sorry. As x goes to the left, y is going down. As x gets smaller and smaller, y gets smaller and smaller. As x goes to the right, your y value is approaching -2, and this is increasing everywhere. Okay, this is our last graphing example. All right, transformations. This has a horizontal compression of 1/2 and down 4. My base is bigger than 1, so I'll do 0, 1, 1b. Okay, and the 1/2, we're going to multiply your x values by 1/2. And you're going to subtract 4 from your y values because it's going down. So that's going to be 0, -3, 1/2 -1, asymptote at a -4. 0, -3, 1/2 -1. That's pathetic. All right. And your range is -4 to infinity. Your y-intercept, yay, we found it already. As x goes to the left, your y value is approaching -4. As x goes to the right, your y value is going up. And this is increasing everywhere. Okay, so there's graphing. All right, so the last part of our notes, we are going to talk about a very special base. This base is called E. Let me pull it up. Okay, I use this all the time in calculus. Oh my gosh, all the time. You'll see it again in pre-calculus too. But the natural base, you'll see this kind of italicized E. And it's used in finance a lot. It's used in statistics. This is known, I don't know if you saw this in honors geometry, the Euler method or the Euler number. Um, it's an irrational number like pi. Like you didn't freak out when you learned that pi was that symbol, and this is approximately 3.14, right? It's rounded, but it's a number that goes on forever, as you know. Well, so is E. And, pi is the relationship between the circumference of the circle and the diameter. Well, E is derived by doing a little bit of calculus and a sequence of numbers. But anyway, my point is E, you don't need to know where it came from right, for this, but you need to know how much it is approximately. I say it's about 2.72. I round it to the hundredths, but it is an irrational number. Okay, so just don't forget that. You're going to use E all the time in upper level mathematics. So here is your introduction to it. Okay, so when we write it, it's a little italicized E, or I don't care if you italicize it in your handwriting, but you need to know it's about 2.72. So when we talk about graphing E to the x, it's going to look a lot like 2 to the x or like 3 to the x. You're going to have the points 0, 1, 1, E, 0, 1, 1b. The parent graph has a y equals 0 horizontal asymptote, 0, 1, and then E is about 2.72. So 1, 1, 2, about 2.72, so it goes about there. So you really don't need to know much about E other than it's approximately 2.72. Okay, we'll do some other things with it, that in this unit. I have to also have a finance question that we're going to do at the bottom of this page. Okay, so here we have a horizontal reflection. So we're going to take our parent points, 0, 1, 1e, and you're going to be multiplying your x values by a negative 1. And so our new points will be 0, 1, and negative 1e. Notice there's no vertical shift, so we have y equals 0 again, 0, 1, and negative 1, 2.72. This is approximate graph, of course. Oh, yikes. Okay, looks something like that. Okay, notice how that we haven't, I don't know, I guess I didn't mention it earlier, but this negative, remember, it changed a growth into a decay. Now it's decreasing, right? Over here, the parent graph is increasing, and when you put a negative on that exponent, it flips it over the y-axis. So now you have a decay problem. So this is just you guys looking at this again and telling whether it is an example of exponential growth or decay. Remember, E is 2.72. We don't care about the number out in front. This is the same thing we did at the very, very first page of this packet. E to the x, this is or e to the 3x is growth. E to the negative 3x, drop that to the bottom, that becomes a positive. And so that is decay. That's like that letter C on the first page that we talked about earlier in this video. Here's another one. So that will be decay also. Over here, growth, decay, and growth. Okay, last thing that we're going to do here is talk about a real life example of using E, and I call it PERT, P-E-R-T, PERT. Let's see, I'll just make sure, yeah, okay. I'm going to pull up my graphic calculator. That's good enough. Okay, sorry. Well, all right, so real life example using E. It's compound interest. If you've ever had a bank account that earns interest, you're very lucky. And as you know, when you put money into something that earns interest, it's getting bigger, right? So P, let's say P is the amount that you put into an account, okay? It's called your principal. Maybe you, in this example, we're putting in $1,000 into this account. And it pays interest at an annual rate. That means by the year, okay? And we talk about this as being R for rate. And of course, we're going to express this as a decimal in our formula. So P is the amount that you put in. E is about 2.72. You are not going to use 2.72. I'm going to show you the E button on your calculator. I'm not going to pull up decimals. The rate is at a decimal, and T is time annually. So if I said 6 months, you would have to do 1/2. Okay, so the amount in your account after the time will be this A. So we have $1,000 times E. The rate here is 0.08. That is an incredibly high interest rate. You will never find that in an account, actually, at least in a savings or a checking. Find the balance after 1 year. So this is just times 1. If that said 3 years, you do times 3. This is going to give you the amount in the account. So let me pull up my calculator. You're going to do 1,000 times, your E button is over here. See this LN? That stands for natural log. But you want the E to the X, so hit second, that button, and we'll do 0.08, and I guess we could do times 1 for fun, and then enter. So you will have, oops, 1,000, I didn't see that very well actually, 83, sorry, this is so hard, at 287, okay, and I didn't round to the nearest cent, I just took it to thousands. So in your account, after 1 year, you now have 1,083.287. Now I know some of you are like, well, if I just do 1,000, times 0.08. That's not how interest works. Okay, that's not how interest works at all. It's not because your account every month or actually every day that $1,000 is growing. Okay, so you can't just take 1,000 and multiply it by the interest rate. That's not how interest works. Interest is accrued over time. So anyway, I mean that's close. 8% of 1,000 is 80. So, but it's bigger because every time your account gets bigger, you're applying that 8% again on a new amount. So I don't know if that makes sense. Anyway, there's a good use of E that we see. We call it PERT. Anyway, have a great day, and I hope this was helpful. Bye.